Hello and welcome back to California Geology. Continue on with earthquakes here. So there's an instrument used to measure the wave amplitude. That's called the seismograph. And remember, the amplitude is going to be half the wave height. And if we kind of look at the seismogram over here, the seismogram would be the printout. So you probably remember that on a seismograph, you'll have these drums that spin around, and then the little pin will show the shaking. And so when there's no earthquake, it's going to be a baseline where there's no shaking going on. But then once you get an earthquake, that pin will start moving, and you want to measure the deviation from the baseline or that amplitude. So how these seismographs work is basically you'll have like a concrete slab that's bolted to the earth. And then you'll have this a sort of stand that's attached to the concrete where you're going to hang a heavy weight. And that heavy weight is basically a mass of inertia, which means it doesn't move. When the earth shakes, that doesn't move because gravity's pulling it down. What's going to move is this drum. The drum is spinning under that mass of inertia. And then when the earth shakes, it's going to spin. You're going to record the amplitude or how much shaking is going on. So this would be one for like the love wave, because remember the love wave is going to move in a horizontal side-to-side fashion. For the Rayleigh wave, because it makes undulations, up and down vertical motion, we need a seismograph that would be something like this. Same concept, except you have to have a spring here to hold up this heavy weight here. Now, so remember the seismogram is a printout, and we get a really important piece of information off the seismogram. And we can determine the distance to the epicenter by looking at this seismogram. That we could also measure the Richter magnitude based on the amplitude of the wave here. So those are really two pieces of information we can get. We can get the distance to the epicenter plus the magnitude of the local shaking, or the Richter magnitude. So the first wave is the P wave, because it's a faster wave. It travels faster by compression and dilation. S wave is a shear wave. It's a little harder to shear material, so it travels a little bit slower. That'll be the second one to arrive. And then finally, the third one, if we're close enough to the earthquake, we'll get the surface wave, either the Rayleigh wave or the love wave. And so to determine the location of an epicenter, we need to determine this S minus P time interval. And so in this example, the way we're going to do it, I'm going to give you a little exercise for you to do at home, and you'll submit it, is first we determine the arrival of the S wave. And in this case, I've got it here. This is 12 o'clock. So this is time on this axis here. So the S waves arrives at 12:01, 12:02.75. So I have it 12, this is the S wave here actually, and this is the P wave over here. I have these backwards. So the S wave is at 12:02.75. The P wave is at 12:01.5, so 12:01.5. When you do the subtraction, you get 1.25 minutes. 1.25 minutes. So anyways, that's the duration, or the time between S minus P. So we'll remember that. We'll come back to that. We'll have to use that for plotting here in a moment. Now, up here in a little bit more detail, the P wave is 1.7 times faster than the S wave. Remember, because it's easier for the energy to travel by compression and dilation than it is by the wiggling of a shear wave for the S wave. At the moment that rupture occurs, both P waves and S waves are together at the focus. As they travel away from the focus, the P wave will get farther ahead of the S wave, and so the SP interval will increase. So in other words, the farther the station is, the recording station is from the epicenter, the longer the S minus P time interval, right? And so we can make a curve. It's called the time travel curve, and what it is, we plot the time on the x-axis, on the y-axis here, and then the distance on the x-axis, right? And so, for example, because the P wave is faster, it's gonna travel in 3 minutes. It travels about 1,000 miles, whereas in 3 minutes the S wave only travels about 500 miles. You see that? So so this curve is for the S curve, and this is for the P wave over here. And so the area between the S and P curves would be the S minus P time interval. So on our previous problem, we calculated a time of 1.25 minutes for this S minus P time interval. So the way to figure out how far this earthquake is from this particular seismic station, we have to figure out where those 1.25 minutes fits between these two curves. And the way to do that, you need to employ a little piece of paper that you can move around on this graph. So the way to work on this is we're going to set this at the ordinate here, and then we're going to calibrate this where we calibrate this to 1.75 minutes. So that would be 1.75 minutes right there. And then once I've calibrated that, I'm gonna move this, keeping this edge parallel to the y-axis and keeping this corner on the P curve. And when I move up here, I see that it fits right about in there. So it fits. So the 1.75 is touching the S curve, and my corner here is right on the P curve. And so if I drop that down, that's about 500 miles. So the epicenter is 500 miles away from this particular station. And so let's say I'm going to plot this on a map. And let's say that station I just measured was over here in let's say it's in South Florida down here. And so if that's our station, then I'm going to, and I just determined it was 500 miles, then I'm going to calibrate my compass. You need one of these compasses to make a circle with a radius of 500 miles, because you know that somewhere 500 miles away from this point is the epicenter. So what I'll do, I set this on my scale here, and I'll calibrate this compass down to 500 miles here. So there's 500 miles right there. So now I've got the 500, and then I just make a circle of radius 500 miles. So I know that somewhere in this area, somewhere along that circle that I just drew there, let's start a little bit darker, that's where the earthquake occurred, somewhere on this circle, somewhere on that circle. This distance, this radius here is 500 miles. So that just tells me it's 500 miles away. So the problem is, in order to accurately locate the epicenter, what I really need, I need 3 of those seismograms. I need 3 of them. So this is actually the problem I'm going to give you. In this case, I have a seismogram from New York, one from Seattle, and one from Mexico City. They're all recording the same earthquake, but note that the S minus P interval are going to be different. So here for New York, Seattle, and Mexico City. And on this particular seismograms, each one of these is a minute. Like for example, this will be the S wave for New York. So the S wave arrived at 9 after the hour, which is right here. That's 9. So 9:01, 9:02, 9:03, 9:04, 9:05, 9:06 and a half. So it would arrive right at 9:06 and a half. So we'll put 9:06.5. Whereas the P wave here arrives at 9:01, 1 minute after the hour. And so in this case, our duration, in fact, an easy way to do it, you can just count it. It's the S minus P interval. So you got 1 minute, 2 minute, 3 minute, 4 minute, 5.5 minutes. 5.5 minutes. So that's a 5.5 minute interval. So again, we'll go back here on our graph, and we'll use our little piece of paper to calibrate it. I like using the Post-it here because I can stick it here, and I'll have it. I won't move. So I'll go down up here to 5.5 minutes right there. So there's my 5.5 minutes. So now I can move this and see where it fits. And it fits right there. So now that's the 5.5 is touching the S curve. This corner is on the P curve. I'm parallel to the y-axis. If I drop this straight down, I got about maybe 20 about not quite 2,500, about 2,400 miles. 2,400 miles is what I get for this distance. So that's for New York, right? So I just got 2,400 miles. So let's actually plot that and see how it works here. So one of the things you'll ask to do is to plot the location of New York. And one thing I want you to notice about this globe is that the longitude lines are curved, right? They're curved. And so are the latitude lines, they're curved. So for New York, I got 40 degrees, 50 minutes. So remember, there's 60 minutes in 1 degree. So this is almost 41. It's just shy of 41 degrees. So if we go up here, here's 40, 41 would be right above there, right? Just a little bit above that 40. Now I have to kind of go along this curve, so it's going to be somewhere in here. So we know New York's going to be over here. And then the longitude is 74 degrees west. So here's 70, 74 will be right around here, right? So here's 70, and so 74 will be so right around here. So then we go up and we're going to intersect at 4 right there. So there's where New York is. So I got 74 and 41. So that's my station. And I know from that station I got 2,400 miles. So now I'm going to calibrate my compass here to 2,400. And then I'm going to draw my circle here. Right? So I'm going to calibrate this 2,500, a little bit less, right about there. So now I've calibrated that to 2,400, and I'm going to draw a circle of that radius. So that earthquake is going to occur somewhere on this circle. So I'll draw a larger circle here. So the earthquake is somewhere on that circle. So what I need, I'll need the 2 other stations and plot circles around them. So the one from Seattle and the one from Mexico. And when I plot them, and I draw circles around. In fact, let's just put Seattle up here. So Seattle is at 47.25 north. So 47 is right here on the coast, and then it's going to be about 122. So yeah, so Seattle's right there. There's Seattle right there. And so when I draw the circle, it's going to intersect in 2 points. But then when I do Mexico City, which is at 19.5, just below 20. And 99.12, so just so Mexico City is basically going to be right there. It'd be a little bit less than 100, and then a little bit less than 20, so right there. So when I draw the circle around that one, they're all going to define 1 point. So it'll be your job to determine the location of that epicenter. So I did the first one for you. You'll do the same thing by doing the S minus P interval for Seattle and the one for Mexico City. Well, we'll see how you do on that.